All right, let's begin. This is CS3510, L13A. The problem is coloring. Recall we're knee-deep in NP completeness. We're now talking about which problems are and aren't NP complete. What does the world map currently look like? Well, we know that from all A and NP, we can go from A to SAT, and then from SAT we can go to 3-SAT, and then from 3-SAT we went to circuit SAT. We can also go from 3-SAT to independent set, and then from independent set we went to vertex cover and clique. And then what else did we do? From 3-SAT we also went to subset sum. And then from set to sum we went to knapsack. We basically showed for the main categories one problem of each. Graph problems, constraint problems, logic problems. The next 3-ish lectures are basically going to be like, what are easy reductions that I know that are kind of interesting but don't take too long. So you can prove there's 10,000 NP complete problems in 10,000 domains that you want to find out about them. You can do so. Packing an optimal Bitcoin block is NP complete. Scheduling operating system tasks, NP complete. Finding a Hamiltonian path, NP complete. So Battleship is going to be NP complete. Minesweeper is NP complete. We'll talk about games in the second half of the lecture, a few of them. So kind of what is something that I want to talk about that's kind of interesting but not too difficult. Some of the reductions are quite technical, is this problem called 3-coloring. So you're given a graph G, and you're asked is a G 3-colorable. Now what is a coloring of a graph? A coloring of a graph is an assignment of its nodes a color such that no two adjacent nodes share a color, right? So the main question about 3-coloring was actually a problem involving coloring maps of the United States, right? So if you have, let's say, Kansas, and then you do, those are probably counties, right? What you can do is, in fact, in considering a partition of land in any kind of shape, and of course, no two counties are supposed to overlap, and the total land mass is supposed to be enumerated by such counties, what you can actually do is describe a graph by having each vertex be a county, and then you may draw an edge between two counties if they have a border. Those two share a border, so I'm going to do that one. Okay. So this graph, coloring such a county map is equivalent to coloring the following graph. And map makers were interested in the question of, I guess that's a little too simple of a map. The map makers were interested in a question of the form, can I always use a certain number of colors to color the states in such a way that I don't color two adjacent states the same color. You know, you want your map to be, if you have two adjacent states the same color, they kind of appear as one state, right? And it took a long time, but basically somebody was able to prove that every map is 4-colorable. It's called the 4-color theorem. You can use it most 4 colors, right? Now we are concerned with, although we concern ourselves with graphs, understand that they kind of, if the graph is embeddable in a plane like this, it's called planar, if you can draw it without a crossing edge, that in the case that it's planar, that this is why we consider the coloring of graphs, right? We asked the question, can you always color a graph with at least 3 colors? A graph is said to be n-colorable if you can color it with at most n colors, right? So for example, give me an example of a small 3-colorable graph. Yes, a triangle. Okay, and I have some colored markers here. Let's hope these work. That's probably blue. That's green. Does that show up?
Yeah.
Okay. and that's black. No two edges are the same color. Okay, good enough. Is a triangle two-colorable? Why not?
Because each vertex is connected to each other.
If you were to use a fancy math terminology for it, why is it the fact that a triangle is not two-colorable? Yeah?
It has an odd cycle.
That is correct. And in fact, a graph is two-colorable if and only if it has an odd cycle. What? If and only if, right?
It's not too colorable if it has an odd.
Sorry, it's not two-colorable if and only if it has an odd cycle. The answer I'm looking for is pigeonhole principle. I'm too lazy for the colors. Let's call this color A. Let's call this color B. Okay? This has to be B and it cannot be A because it is next to it, right? Pigeonhole principle. There's three vertices all touching each other, but only two colors. So two of them must be the same color, right? So this one must be A or B, and whatever it is going to touch one of the others. So this is not two-colorable, right? And in fact, we will prove that the problem of three-coloring a graph is NP-complete. What about the problem of two-coloring a graph first? Is two-coloring a graph NP-complete?
Possible.
In how fast? It's polynomial time. And so in fact, it is this is called three-coloring. Two-coloring is in fact NP. Why? Maybe. I don't remember. Yeah?
Yeah.
Yeah.
You just run BFS and check if like the nodes are connected or not.
Exactly. Find your odd cycle. Not too difficult to do. This is the moral of this. What I'm mentioning this for is every NP-complete problem actually has polynomial time subproblems. 2-sat is NP. 3-sat is hard, but 2-sat is easy. Finding, for example, a vertex cover of a tree, I'll tell you, is easy. Finding a clique or an independent set of a tree, also easy. Or even independent set of a bipartite graph, easy. In general, hard, but in specific cases, it can be easy. So every NP-complete problem sometimes has, they all appear to have a very easy subproblems. But two-coloring a graph can be done in P. Three-coloring a graph, I claim, is NP-complete, in the sense that this is hard, but this is easy, right? So as a phrase as a decision problem, it's like, is this graph three-colorable? Can you assign the vertices in such a way with only three colors that no two are adjacent, right? That's the question we ask. Right, so first off, to prove anything in this unit, we always need to prove something is an NP, and then we need to prove it's NP hard. So first we need to prove it's an NP. Let's try to argue why is three coloring in NP?
Because once you have a coloring, you can check it.
That's as good as the answer could ever get, but if we were to fill in the details, our verifier takes as input the graph G, which is the problem instance. Here it's just a graph. If it was a graph number, if it was two graphs, you would have to make sure that it takes as input that. And then it also takes in a witness, which should be, what is the witness?
A coloring of the graph.
How would I encode that?
A list of the nodes. Three lists, one of each color, and all of the nodes are in one of those three lists.
Let's say of size n, right? The ith vertex is v of I 0, 1, or 2. Let's say those are the three colors. So then we could say for vi, vj in E, check, what would it be? W of I does not equal wj. Then that is a solid three coloring of the graph. Some other syntactic sugar would need to be done. Check that there are three colors and not four colors. Check that there's exactly n elements in our witness, all this other stuff. Either way, this takes approximately time, what? What? Yeah, if I were to give it, if I were to ask for an upper bound, what would it be? Like an actual, it's n squared. If it's about the time of E, so that's a v squared, n squared, right? Per edge, there's at most n squared edges. So it is an NP. Now we want to reduce from some problem. We've sufficiently proven that it is in NP. By the way, why do we care about proving something is an NP? This is something I think I have not mentioned explicitly. We want to prove, for example, two problems that could be said to have the same difficulty if this is true. Would you agree? this is the polynomial time reduction is a relationship that shows hardness. So if you could show both directions of this, you could say they're as hard as each other, right, up to a polynomial time reduction, right? So what does showing a problem in NP really give for you? Because we've proven that 3-column is in NP, by Cook-Levin, we know that there's a reduction from all of NP to SAT, including 3-coloring. So by proving that 3-coloring is in NP, this actually implies that there's a reduction from 3-coloring to SAT. In fact, let's just, let's say 3-SAT. So in fact, 3-SAT is, by showing it's an NP, you've actually shown it's easier than 3-SAT, which is, you show it's an NP so you don't have to do 2 reductions. You get to use Cook-Levin for free by just giving the verifier for it. And Cook-Levin tells you this for free. Now we want to prove the other way. Once we do this, so we only need to do this and this. And that shows for us the same thing as these, right? That's kind of why we do it in NP. We care it's not too hard. It has to be at least polytime verifiable. But this is kind of the reason. That's why all these are, we say they're in a suicide pact. They're all the same, right? Questions on that?
So basically, in order to prove it, you have to, we're basically trying to see, is this as hard as all the other NP problems? And
That's the point of every NP completeness
what we
reduction.
have to do
Yeah.
is show a reduction both ways.
You don't have what I'm saying is you don't have to show the reduction one way by
This
just
is
showing
the
it's an
trick
NP.
that lets it so that we can skip the second reduction.
Yeah. But you need to do both. Right. So now we want to perform a reduction from 3-SAT to 3-coloring. Now, it's common that you actually don't want to reduce from 3-SAT. You want to reduce to a closer problem that you already know. For example, here's our big tree of the reductions. We reduced from 3-SAT to independent set, and then from independent set to clique. It's not necessarily true you had to do that, because you could technically go from 3-SAT straight to clique. That reduction exists. In fact, it was done before this one was done. But it's just simpler to go from a problem you already know. So although 3-coloring is a graph problem, you may think, let's reduce from a graph problem, because that's kind of easy. That's not terrible intuition, and that is actually really good intuition. But the problem is, I don't think it really works here for this in this specific case. So we actually would want to reduce from 3-SAT. But note that if you want to reduce, for example, constraint problems, start with subset somewhere in AppStack. If you want to reduce graph problems, try to look at independent set, vertex cover, or clique. If you want to do logic problems, SAT problems, circuit problems, try 3-SAT or SAT, right? So start with those before looking just straight from 3-SAT, because you're going to have to repeat some work. So intuition-wise, we're going to try to, intuition-wise would tell us, like, try the graph problems first. But I'll tell you, for this one, I don't think it's that simple. So we're actually going to do the reduction directly from 3-SAT to 3-coloring. Okay? So how is this reduction going to work? We really want a graph to be 3-colorable. We want to create some function that says that phi is is satisfiable if and only if some graph G, which is constructed from phi, let's say, is 3-colorable. Right? That's kind of what we hope to prove. So what we really need is, if we break down SAT, there are a few parts, right? First off is the part that variables must be assigned, and they must be assigned consistently, right? For any x, it must be the case that x is true if and only if not x is 0, right? We need that to hold, first of all. Second of all, we need something analogous, some kind of OR gate analogy, not a gate necessarily. And we also need some kind of AND gate. So I'll call it instead of an OR gate analogy, I'll call it a clause gadget. A gadget is a technical term. It's a doohickey that does the thing for you. It simulates whatever a clause was supposed to be. And then you need some kind of AND gadget. Right? If you can have these 3 parts, if you think of every problem like a programming language, if you can figure out how to express these 3 parts as subroutines and then correctly routine them up together, wire them up, then that problem can simulate 3-SAT. It's probably NP complete. So what does it mean to use a graph coloring like a programming language? That's nonsense, but it can be done, and we'll show you how to simulate these 3 parts, right? So it's going to turn out that our coloring itself is going to correspond to the satisfying assignments, right? So there are, for every variable, there's 2 possible satisfying assignments, but there's 3 possible colors. So let the colors be T, F, and S. So this would be like tangerine, fuchsia, sepia. No, I'm colorblind. Scarlet, sapphire. There we go. It's blue. Okay, those are 3 very different colors. T, if a node is colored with T, we want that to correspond to its assignment being true. F, we want to correspond that to be that variable being false. And then S is just going to help us control T and F. That's really the point of it. S is nothing. So notice immediately though that it doesn't really matter what the colors are, because if a graph is 3 colorable, it's not uniquely so. Why? Permute the colors is going to be an identical coloring. It doesn't really matter that this node is red and this one is blue. For example, let's say this is red, blue, and green. This is an identical coloring. Red, blue, red, green, right? Those are all colorings of the same graph. It doesn't really matter. But just for convention, we'll suppose that this is what we hope them to correspond to. Notice immediately, though, we have something great. What is it? A graph is, the smallest 3 colorable graph is a triangle, right? So in fact, by smallest, we also mean that it's not 2 colorable. So if we instantiate a triangle, we are forced to color with 3 colors, right? Important in every reduction is that we don't actually know if the formula is satisfying or not. But the graph will be colorable if the formula is satisfying. So we don't actually know when if our graph is 3 colorable or not. But it's the satisfying assignment, if it exists, to phi will correspond to a coloring of this graph. So first, we need to get this first property here, right? No, this one. Where a variable and its negation cannot both be assigned. If we have the case that we have a triangle like this, we know that it must be colored with 3 distinct colors, right? We also know that I'll just draw it. If we have x1 and not x1 like this, and we link them together, they must be colored with 2 different colors, right? So let's create a bunch of gadgets like that. Okay? At most, one of these can be T, and the other one could be F or S. We don't want any of them to be S. Same thing here. It could be the case that this is T, and then this is T, but then this is F, and this is S. That's not quite what we want. So what we're going to do is connect all of these to some same node that we hope is colored with S. Okay? Now, we cannot force a coloring. We cannot say this node has to be colored S. But we can permute the color, so it doesn't really matter. So suppose it's colored S. If this node is colored S, this one must be colored T and this one must be colored F, or they're swapped, doesn't really matter. Just suppose it's that coloring, right? We can wire up these kinds of gadgets in such a way that each of these will correspond to x1 or not x1, x2 or not x2, and so on. Now note, though, you cannot have x1 the same color as not x1, x2 the same color as not x2, and so on. And if this ought to be colored S, exactly one of these must be colored T, and exactly one of these from each must be colored F. So do we agree that this is a way in the coloring to simulate at least this first property here? Questions on this? So now we need a clause gadget. So what we really need is an OR gate. We need to figure out a way to OR 2 things together. So we want some kind of subgraph for, let's say, let's just do a single OR gate first. So for example, xi or xj, which is to be f if xi, xj both f, and is to be, could be t if xi, xj either are t. We don't want it to be the case necessarily that this kind of gadget we're going to make forces a color on the output, because it actually won't be possible. We want there to exist a coloring if there exists a satisfying assignment. Note that there are many unsatisfying assignments to a formula. We want those to correspond as well to the incorrect colorings. But we want there to be a correct coloring only when one of those must be t. So what we're going to do is, for each of these, we're going to wire them up in the following way. Suppose I made copies of them here. They're not different nodes. They're the same node. Let this be xi. Let this be xj. Okay? Now to wire them up in an OR gate-like way is just going to look exactly like an OR gate. It's not expected that you could come up with something like this yourself. But this is, in fact, the OR gate. What color is this as a function of xi and xj? So let's call this v. Both xi, xj are colored with f. Okay? If they're both colored with f, what could this be? This could be t or s. What could this be? Yeah, but it's going to be the opposite of that. So let's call it s or t. These two must not be f, but they must be opposites of each other. So one of them is the t, and one of them is an s. We don't know which one. So what must this be? It has to be f. There's no way to color it not an f, given these are both f. So we see if they're both false, the output of this gate is a false, right? Every NP completeness reduction is, when you get into it, it can be kind of fun because it's just solving a little puzzle, okay? Fine. Now with any, if either xi, xj are t, does there exist a coloring of this that's valid? Let's try it. Hold on, I'll do it over here. Let this one, let's say xi, xj. Without loss of generality, let this one be t. Okay? This one could be f or s, but of course we can assume that because it's wired up here, we can just assume it's going to be f. It's not a problem for us. And then just permute f with s. So let this be f. If this is t, what could this be? This could be s or it could be f. What could this one be? This could be t or s. But it could not be both. So either this is s and then this is t, or this is f and then this is s, right? So they both couldn't be s. That would not be a valid coloring because they're connected, right? So given that, what could this be? If these are s, if this is s and t, then this gives you f. This must be, wait. Yeah, if this is s and this is t, then this must be f. But if this is f and this is s, then this must be t. So it's not true that it's forced to be t, but there is a coloring that is t, because this would have to be made, you make sure you do this part correctly, and then that would color this one correctly. So it's not the case that its color is forced, but there exists a coloring. There is a coloring. And that's good enough, because we want there to exist a satisfying assignment. So as long as there's still a valid way to do it, we count that. So we've done it for an OR gate of size 2. Now a clause, though, in 3SAT is of length 3. How could I do this in the 3 variable case, the 3 literal case, excuse me?
Do another copy of this, the other 2 variables, and then attach the outputs.
Does that work? Yeah? 2 OR gates is, okay. Questions? Kind of obvious, right? It composes with itself. This is going to have an output of F, right? An output of F. The node is going to be colored F. So if these are both F, this is F. So if this is F2, then we get kind of a recursive property there, right? What is a circuit but a composition of its gates? So by composition properties, this is going to also be an F when this is an F and this is an F. And this was an F because these two were Fs, and so on, right? So if one of these at least is a T, there is a way to color this with a T, because let's suppose these were F and this is a T. F and T here could give you SFT, so it's fine, right? So there is a way to do this clause gadget. So we have sufficiently completed the clause gadget step. Questions about that? And also, there is no formal theory like you need exactly these three things. It's just like an intuitive thing to get 3 sat in there. Yes? If both of them are true, would it work? Let's try it. I'm not sure. Maybe it is working. Let's see. Let this be T. Let's just double check. If this is T, this could be S or F. This could be S or F, but the opposite. So this is either S. Wait, no, the opposite. So this is either F, S and F, which would give you T, or this would be F, S, which would also give you T. So in fact, it's forced to be T, if both of them are true. Yeah. It's actually same reason as the F's. They're both. If they're both false, it must be false. If they're both true, it must be true. If one of them is false and one of them is true, there is still a way to make it false. Excuse me, a way to make it true, and that's sufficient for us. Does that answer the question? Yes. Okay. More questions on this clause gadget? Okay, now we need a way to wire them all up. How are we going to make an AND? Let's think about it for a second. Let's take a moment to brainstorm. How can we make an AND? This is an OR. How can we do an AND gate? Yes?
The same thing, but the first layer of nodes is fully connected to the second layer of nodes. I don't know if that makes sense, but the ones on the left, both of the ones on the left are connected to both the ones in the middle. I think that.
Oh, you mean like this?
You draw the diagonal lines. Yes.
That might work. I think I have a simpler explanation, though.
Okay.
There might be a problem with that later down the line, but that would work. I think there's a reason it won't work in a complicated way, which I'll say in a second. Question?
Similar to that, like if you have in systems, you can negate the inputs to get AND for an OR. So if you connect that to the second layer, then you're saying not F.
If we had some sort of negated thing, then you could negate clauses and OR those by De Morgan's. Interesting. So how would you do a NOT gate?
No, because that's only takes one input, one output. Like really.
I think you could do a NOT gate. I don't know how. That's what I'm asking.
Oh,
It could be like this. Almost, right? If this is T, this would be F or S. Yeah. Well, if you could get rid of the S by connecting it to something that you know is colored S, right? So if this is S or F, unless you know this is going to be an S, and then you know it's going to be, this must be then F, right? If you could do that. So basically what we're going to do is generalize on top of all that. It's sufficient for us to ensure that every clause has the same output coloring, right? This is the output node of the clause. So we just need to make sure those are all the same color. So what we're going to do is just connect them all together and then connect them to a triangle that we know is going to have two colors of each. So recall our original triangle that looked like this, right? What do we do? And we connected everything to the S node. Right? Something like that. Now, if we want the output of each, we have a bunch of clause gadgets like this, right? right? Let those be the outputs of each clause. We can ensure that they're all a value of t by connecting them to values that are both s and f. If we connect each of these outputs to s and f, then it must be the case that they're all t. Right? So we connect all of them to the S and F, which is the base triangle. These are the xi naught thing, right? Just connect them all to that triangle, and that must, if there is a coloring, it must be the case that those are all T. Okay? This is we're done. That's the output graph, right? Questions? The reduction should be everything I said out loud, but let's just quickly kind of review. Let phi be in SAT. Let's say 3 SAT. Then there exists a satisfying assignment. Why is it the case that the graph is 3 colorable? It's kind of a long answer, right? Color xi, xi naught for each I appropriately. The remaining graph can be consistently colored. So we know that G is in 3 coloring. Now, why can the rest of the graph be consistently colored? Pretend I said all this stuff we talked about with the ands and the ors and the gates and everything, that all kind of works out, right? If it's the case that every at least one of xi or x, if it's true that for each clause, each one is satisfied in some way, then for each clause gadget there is a coloring that colors the output node to true. So then therefore these are all colored true, and the rest of the graph can be done consistently, right? I could perhaps mention that each clause gadget could be colored in such a way with the output node being colored true, and therefore the coloring is consistent, and so it's a 3 colorable graph, right? That's what I would say if I wanted to write all that down. But consider the reverse case. Should we do Q implies P or not P implies not Q?
Not P implies not Q.
Why?
The other one would just be a mess, I think.
Suppose G is 3 colorable. Why does that coloring correspond to a satisfying assignment? I agree.
But the correspondence we made was like a heavy construction. Not every graph will fit that.
I agree. So let's suppose phi is not in 3 SAT, right? Wait, we want to do not P implies not Q, right? Yeah, okay. Suppose phi is not in 3 SAT. Then for each assignment, some clause is unsatisfied. Then for each coloring, some clause is always outputting F as a color. In the clause gadget construction, if a clause is unsatisfied, this is forced to be F. This is forced to be F, yes. So it forces itself to be F, yes. It cannot be S. Is always outputting F. And it doesn't actually matter for the proof. And then what's our contradiction here? But it is adjacent to a node of the same color. Thus, G for each coloring is not in 3 coloring. Right? Don't forget where these inputs come from. Here is, let's say, x1. And if this is x1 in this clause, and then this is right? This is actually there, and so on, right? So the coloring here that forces these to be T and F forces these to be colored accordingly. So in fact, what you're going to get is that this is going to be, let's say if this is an F, it's going to be adjacent to an F. That's going to be a problem for us, right? Even up to permutation of the colors. For each coloring of this graph, each one of them must have two colors that are adjacent to each other, that are the same. Therefore, there is no way to color the graph that's three-colorable, right? Really, and this is a little different than when I do proofs on the board than what is expected in the homework, because I say things out loud and I spend the whole time explaining, but that really is the proof, and really that's what should be, everything I said out loud should have been written down and is what should be submitted. Not that you'll have a reduction that's hard, but this is not a good example of like how to write a very formal reduction. But there's one more step we forgot.
Polynomial time.
Why can the reduction take polynomial time? I don't need a very strong answer.
How many clauses can there be in a set?
Well, let's suppose you have n literals, maybe even n variables. Let's say you have n variables. A clause is at most a variable, at least a variable. So the number of clauses is upper bounded by the number of variables. You assume that there are not terrible things, such as x1 or x1 and x1 and x1 and x1 and x1, right? And even if that was the case, you could detect this in polynomial time and reduce to a smaller, back to the original case, right? So polynomial in the number of vertices, the vertices are a polynomial number of the variables and the clauses. Each clause, there's a gadget per clause, and there are gadgets per variable. And then there's a few edges to wire all that up. Either way, it's approximately, perhaps even linear size in the size of the formula. You don't have to say too much more than that, but then the graph can obviously be constructed in polynomial time. In fact, the only time you would have a reduction that's not polynomial time, if it had to brute force search for something, which is impossible, which should never be allowed. But it's a simple graph that's constructed on from the simple formula, right? So this is sufficient for us to prove that three coloring is NP complete, right? We proved this in NP. Okay. Now three coloring is hard. What about two coloring is easy? What about four coloring? Hard or easy?
Or
Why?
probably equivalent to 4 sat.
Interesting.
Oh, no, it's not.
Is it not? So I'll tell you, there's a big theorem of graph. Every planar graph can be four colored. I don't know if that's an if and only if, but but not every graph is planar. So if you can detect if a graph is planar, then you can definitely four color it.
I think 4 sat. I mean, 4 coloring. We replaced the. Actually, I don't know if it was the same.
Question? No? Okay. What about n coloring? Forget 4. I ask for g comma n such that g is n colorable. First off, n coloring, is it in NP? Why?
Basically the same verifier, except you have different.
Basically the same verifier is the best answer you could give. Oh, I'm out of focus. Hold on. Okay, there we go. N coloring is in NP. Basically the same verifier, a little different check. Now it's a function not just of the graph size, but of this number n, which you would loop up to that number, so it's okay, right? G has at most n vertices anyway, so fine. Why is n coloring NP complete? I'll even give you another one. Give me a reduction from 3 coloring to n coloring. Forget the 3 sat. Our reduction is going to take out input G and output a number, graph number pair. G prime, let's say n. What correctness property should we observe? If F is supposed to take on G, what should it output? This is easy. This one's an easy reduction. This could be an extra. This is a previous exam question, by the way. Yeah. Yeah. If G is if G is 3 colorable, G is n colorable when n equals 3. That's it. I mean the correction. Okay, let G be 3 colorable. Then G comma 3 has a 3 coloring, which is the same 3 coloring of this. Okay. Let G comma 3 be 3 colorable. Then G is 3 colorable, so G is in 3 coloring. Done. If someone comes up to you and they claim they can solve n coloring, fine. Then they can also solve 3 coloring. So you say solve 3 coloring for me in polynomial time, so they can solve this NP complete problem efficiently. It's a generalization that's the same hardness in some sense. So you don't have to think too hard about some reductions because they come for free if you generalize in the right way. N coloring is harder than 3 coloring, but no, it's not, because it can still solve 3 coloring, and 3 coloring is hard. So that's the moral. It's still as hard as 3 coloring. Up to polynomial factors, but same thing. So a polynomial time algorithm for 3 coloring gives you a polynomial time algorithm for n coloring, and of course vice versa. It's sort of the moral here. This is a previous exam question, by the way. So this is in fact a true and false level question. So hopefully you guys can get this. Any questions on coloring? Okay, take a break.